Alright, class. This is our last video for the book stuff, at least, and I'm gonna be square with you. I'm gonna tell you how things really are. So this is the truth. You finally get the truth, and the truth is molecular orbital theory. And well, the truth I've been telling you the truth that bonding actually comes from the electronic magnetic field and form new energy. Well, that's a energy levels. So, but I'm going to tell you it's actually something. This is the approximation. It's called LCAO, or what happened here? Linear combination of atomic orbitals. Else, this is the approximation called LCAO, linear combination of atomic orbitals. Now, this may seem really funky, but this is how it mostly works. So, look at hydrogen, for instance. Hydrogen, what happens is that the two hydrogen nuclei or atoms approach each other, and now the electrons feel each other's electronic magnetic field, and what they do, so you have two energy levels here, what happens is, and this is the potential energy, they split. They form new orbitals. They form a bonding orbital here and an anti-bonding orbital here. And we mentioned signs plus and minus for the phase of the wave functions. You have a bonding orbital down here and an anti-bonding orbital up there. And you can look at it in terms of the waves. So if they constructively interfere, the waves form a bonding orbital, and then if they destructively interfere, they form an anti-bonding orbital. And you might also see this. So this is a sigma bond, so it's between the two atoms. So sigma bond, and you might see G and U. The star means anti-bonding, so this star up there, that means anti-bonding. And the G means Gerada, and the U means Ungerada. That's German for, so Gerada means symmetric, Ungerada means anti-symmetric. So upon inversion. So it's upon inversion. If you see here, if you invert from here to here, going across the center, that is not symmetric. Whereas through the center here, it is symmetric. So that's a Gerada, and then the antibody is Ungerada. Okay. And that's not on this class. That's beyond this class. Bond order. The bond order is a number of bonding electrons minus the number of anti-bonding electrons divided by 2. Okay, so let's look at hydrogen then. So hydrogen atoms approach each other. So these atomic orbitals go away and a new molecular orbital is formed. So that's really what happens. They go away, and it forms a bonding orbital, and since this bonding orbital is lower in energy, they bond. What about helium though? Helium here, if so, say two helium atoms approach each other, they will form a bonding anti-bonding orbital, but then the electron density in the anti-bonding orbital, so the bond order, so BO means bond order. Number of bonding 2 minus number of anti-bonding 2 divided by 2, this is 0. So a bond order of 0 means the molecule doesn't form. So helium-2 does not form. What about helium-2 plus? Say if we had this molecule, say if we were somewhere really hot, like the sun, and instead of this, what if we had that? What if we had helium-2 plus? Now the bond order is 2 bonding minus 1 anti-bonding. This is a bond order of a half. So molecular orbital theory, we predict this molecule would form. You know what? It does form in the sun. So, oh, I even have it right here. So we will see helium-2 plus in the sun. So this is something that molecular orbital theory predicted and actually does form. Okay, what about lithium, dilithium? If you're a Star Trek fan, guess what? Dilithium does in fact exist. So dilithium exists in the bond order Bond order of dilithium is 2 bonding, 0 non-bonding over 2. Bond order is 1. What about diberyllium? So and lithium has 1 valence electron each, so 2 valence electrons. Then for the bonding, beryllium has 2 valence electron each, so 4 electrons. This means the bond order, this is 2 minus 2 over 2, which is 0. Diberyllium does not exist, or at least it doesn't form. Diberyllium plus does. Has a bond order of 1/2. Okay, so it's easy to understand with the sigma bonds and the s orbitals. What about p orbitals? So p orbitals, you look here. So 2 p orbitals can form a bonding and anti-bonding sigma bond. Okay, so these are the ones that are internuclear axis, and then the y's and the z's, they can form a bonding and a non-bonding. And where the sigma bonds, the bonding orbitals were symmetric upon inversion. The pi bonds are different. This one here, the bonding pi orbitals are Ungerada, they're asymmetric upon inversion, and the anti-bonding orbitals are symmetric, they're Gerada, they're symmetric upon inversion. So you study, this is important when it comes to spectroscopy, specifically Raman spectroscopy. Okay, so same thing then with the other orbit, so whatever one you want to call Z and Y. Okay, so let's see if you're following. Which one has the highest bond order? Think about this for a second. So here is beryllium 2. This has a bond order of 2 minus 2 over 2. This is 0. So plus 1. So plus 1 is going to be 1/2. Plus 2 is going to be 1. Plus 3 is going to be 1/2. So beryllium plus 2 has the highest bond order. Okay. So now we've mentioned all the sigma bonds here, kind of thing, with the s orbitals. Let's go on and talk about the p orbitals. And here, if you look at this chart here, potential energy is the y-axis, so the higher up, higher potential energy. So when you have the boron, carbon, nitrogen, oxygen, fluorine, and neon, this is the structure of the molecular orbitals that form. And there's a splitting in here. You can see after nitrogen, oxygen has a new set of orbitals. It changes kind of the order of the and strengths of the sigma and pi bonds. So the pi bonds are stronger for boron, carbon, and nitrogen, but their sigma bonds are stronger for oxygen, fluorine, and neon. The reason for that is, again, just the electronic and magnetic fields. They interact and they form, the energy levels there are lower. So if you were to do the quantum mechanical calculations, you would find that to be true. But that's above and beyond this class. So if you look here at boron, boron has 3 electrons, 3 valence, so there's 6 electrons. So 2 in the bond and the sigma s, 2s, 2 in the anti-bonding, and then Hund's rule applies. Lone pair there in the, or let's just say 2 electrons in each of the open 2p pi bonding orbitals. So then 2 more electrons for carbon, 2 more for nitrogen. The bond order is the number of bonding minus the number of anti-bonding over 2. So diboron has bond order of 1, dicarbon bond order of 2, dinitrogen bond order of 3, dioxygen bond order of 2, difluorine bond order of 1, and dineon is a bond order of 0. And this is actually where molecular orbital Okay, let's do some of this stuff. Molecular orbital theory. Draw the molecular orbital diagram for and determine the bond order of the N2 minus ion. Do you expect it to be uh, uh, do you expect the bond to be stronger or weaker than the N2 molecule? Is it diamagnetic or paramagnetic? Okay, lots of questions. N2 minus, this is 11 electrons. So N2 minus, this is 11 electrons. 5 from each of the nitrogens, minus 1 is then the 11, so the minus 1 charge. So let's put 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Bond order is how many are bonding. So you get 2, 4, 6, 8 bonding. So 8 bonding minus 2, 3 non-bond or anti-bonding over 2. This is equal to 5 halves, 2.5. Okay, so bond order is 2.5 for N2 minus. Compare this to comparing it to plain old N2. So this is N2 minus. The bond order for N2 is 8 minus 2 over 2, which is 3, N2. So the bond order, do you expect the bond order to be stronger or weaker? It's weaker. So it is weaker, and is N2 minus, so let me go back. This is N2 minus. Is it diamagnetic or paramagnetic? It's paramagnetic because it has this unshared electron right there. Okay? So what about this? Is O2 plus, is this diamagnetic or paramagnetic? Think about this for a second. So the number of electrons, we're going to have 2 times 6 for oxygen, minus 1 for the plus 1. So this is also, this is 11 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And because of that, that unshared electron is paramagnetic. Okay. So what about other things? What if we've had homonuclear, which means homo means same. Homonuclear. What about heteronuclear? When you have heteronuclear, there's no rule you can follow. You have to do the calculations or have a computer to do it. Okay, so what happens is that the energy levels are different, and now the molecular orbitals that form, you can't just look at it and say, oh, okay, this is the way it goes. You have to just sit down and do the quantum mechanical calculations and bring them out. But here's nitrogen monoxide here. This is the molecular orbital diagram for that, and here is it for hydrogen fluoride. So here's another one, and you can have non-bonding orbitals in molecular orbital theory too. They just don't change. The atom keeps them, and they're not necessarily lone pairs. But they stick around the atom. Okay, what about polyatomics? So, and again, this is above this course. Well, the book mentions it, but this is not necessarily tested on polyatomics. So, polyatomic means that many atoms. Well, it's more than 2, I should say, more than 2. And the way that a molecular orbital theory works in this, at least linear combination of atomic orbitals, you have if they're here, these are all actually. If you have here, these are all in phase. Here and below, these are all in phase. You have, this is the lowest energy level, and you're going to have 2 energy levels here. So I'll do the blue is positive, and then the yellow here is negative. And you get a node. You get a node right there. You can get a similar one and have a node on the other side. So there's 2 degenerate orbitals that way, and then you have just the everything out of phase this way, and the linear combination of these atomic orbitals give you a very high energy kind of a anti-bonding orbital. And if you were to populate the electron density like this, as I've drawn it, you have something here. We call it a HOMO. That means highest occupied molecular orbital. And then here, this is known as a LUMO, lowest unoccupied molecular orbital. So that's something you can go on if you go and study more organic chemistry. They'll talk about HOMOs and LUMOs. So, okay, and the last thing I will talk about is, and if you have been doing the homework on mastering chemistry, Tro, the author, talks about this as well, about the toxicity of carbon monoxide. So, but he uses a geometric argument. I'm going to talk about bonding. Here is my, Tro has much better simulations than I do. Here is my my artist's rendition of the hemoglobin molecule. Okay, so it's an iron with a bunch of black carbon all around it. Okay, so an iron has the DZ orbital, the DXYZ orbital, the kind of clover leaf looking one, and carbon monoxide has an unused open pi star orbital. And these can actually go and they can bond. This open orbital can grab electron density away from the iron. And actually it weakens. So when the carbon monoxide comes along, it will grab electron density away from the iron and it'll weaken the bond. So that's one way. What's one way you can break bonds is to add electron density to it. At least add electron density to the anti-bonding orbital. Adding electron density to the anti-bonding orbital will break the bond. So, but the carbon monoxide weakens with its bond, but it bonds very strongly to iron. And the problem with this is it bonds more strongly than oxygen. So because of that, the carbon monoxide and cyanide works the same way, will bind up all the hemoglobin, and then the patient who has this happen to will die, or start to suffocate, I should say. Suffocate and perhaps die. Okay, so that is the back bonding. So from that, and that's so the pi star orbitals, they mean something, and they can actually physically mean something to people in life and in medicine. So okay, well, we are done for the stuff that's in the book. So I got one more video for you. So don't go just yet. So stick around for one more. And I will see you next time.